We've talked about chemical reactions, and we said that a chemical reaction is started only when the reactants come into contact. Okay, so we can write out our chemical reactions and we can balance them, but they don't actually start until we mix our reactants together. Think of this like when we mix vinegar and baking soda together before they bubble up. Okay, when I have vinegar by itself and baking soda by itself, neither of those are reacting. So they have to come into contact with each other to start the reaction. But what determines when the reaction finishes? Okay, how do we know when the reaction is going to be done? What controls that? So let's think about a balanced reaction. So here we have the formation of carbon dioxide, where I take carbon monoxide and react it with gaseous oxygen and create carbon dioxide. So from our balanced equation, we know that if I take 2 moles or 2 molecules of carbon monoxide and I react it with 1 mole or 1 molecule of oxygen gas, I create 2 moles of carbon dioxide, or 2 molecules of carbon dioxide. So once I've used up 2 moles of CO and 1 mole of O2, then my reaction finishes because I've created 2 moles of carbon dioxide. Okay, so once I've used up all of those reactants is when my reaction is done. But if we're thinking of the real world, if we're chemists, we're thinking in a lab setting, our reactants are usually not present in perfect stoichiometric amounts. Okay, when we're making a volcano with vinegar and baking soda, we just dump baking soda in there and pour enough vinegar till we start to see bubbles. But sometimes we have baking soda left over because we didn't measure exactly perfect amounts for those to be reacting completely. So this suggests that one reactant may be completely used up, while another will have some left over. The reactant that's used up first in the reaction is the limiting reactant, because that limits the chemical reaction, how far the chemical reaction can go, and how much product we can create. So it is what limits the reaction. The excess reactant, or reactants if there's multiple, are those present in quantities greater than necessary to react with the quantity of the limiting reactant. So it's whatever is left over. So in our example, we have a lot of excess baking soda, and our limiting reactant was the vinegar. So I've used up all of that vinegar to make my bubbles and make my volcano, but I have some extra baking soda left over that's unreacted. So what do? We keep adding our vinegar. So I have a few real-life examples of limiting reactants. One of those is making s'mores. Okay, right now I'm in the summer, so this is peak s'more making time. And when we're making s'mores, we always somehow end up with a lot of graham crackers left over, and we usually run out of chocolate first. Okay, and that just depends on how much we buy of each. When we buy a box of graham crackers, there's enough graham crackers to make about 20 to 30 s'mores. When we buy a bag of marshmallows, there's usually just about enough to make that many as well. But when we buy chocolate, if we don't buy enough, then we can't make as many s'mores, because a s'more without chocolate is just disgusting. So we can say that whatever piece of the s'more that we have in lesser quantity is going to limit the number of s'mores that we can make. And that's why we always end up with graham crackers left in our pantry that just end up going bad, because we're sitting there eating most of the chocolate anyways. Another good example of this is hot dogs. Do you ever notice how hot dogs are sold in packages of 10, but the buns come in packages of 8? That doesn't make any sense. The buns are going to limit the number of hot dogs that we can make. A good hot dog where we have a bun and a hot dog in it. So in chemistry, we see the buns as the limiting reactant. Okay, so our equation would look like this. We have 10 hot dogs and only 8 buns. So I can only make 8 good hot dogs, and I'll have 2 bunless hot dogs left over. Okay, so we usually end up not eating those anyways. So before we jump into how this relates to chemistry, let's just think of what a limiting reactant is in terms of a chemical equation, or an equation at all. We won't even say it's a chemical equation. So Consider this reaction. 2A plus B goes to C. In the diagram here that represents this reaction, which reactant, A or B, is limiting reactant? So the limiting reactant would be the one that's used up first. So we know that 2A molecules, oops, that's B, sorry, 2A molecules combine with a B molecule in order to create our product of C. So what we can do is start pairing up our molecules here to see what's left over. So I have 2A's with a B, 2A's with a B, I have 2A's with a B, and then I have an A with a B. So I can make 1, 2, 3, 4 C's from all of the A's and B's that I have, and what I have left over is a B. So what's left over, that's my excess. So B is my excess, therefore my limiting reactant is A. Because I used up all of my A molecules, my green molecules, I used them all up, I couldn't do anything with my extra B molecule. So I have excess B left over because my reaction was limited by my reactant A. Okay, a similar problem. Reactants A and B. A is red, B is blue. Combine in the reaction vessel shown to form a single product C. According to the equation 2A plus B goes to C, which of the following scenes represents the contents of the reaction vessel after the reaction is complete? Well, this is similar to what we did before, we just have a slight change in color. So we know that 2A's are going to combine with a B, so B is blue, A is red. So what I want you to do is pause your video and make up your C molecules by connecting A's and B's in the correct proportions, and try to find which of these products or which of these options would be what the reaction vessel looks like after the reaction is complete. If we keep going with our circling, we have 2 A's mixed with a B. We have 2 A's that can mix with a B. We can have 2 A's that mix with a B. So when these combine, they're going to turn into purple, which is C. We would have 1, 2, 3, 4 purples, and what's left over is a blue. So we have 1 blue left, which was B. So this suggests that B is excess, A is limiting, and our product, or the reaction vessel after the reaction is complete, should have 4 purple dots and 1 blue dot. Well, our first example here, A, just has all purple dots and far too many of them, so that one's wrong. B has a lot of purple dots and 1 blue dot, but it has too many purple dots. Okay, remember these A's and B's are combining to make one single product. Okay, it's a combination reaction. So we have too many purples here, so that's wrong. C is looking like a good answer. We have 1, 2, 3, 4 purples and a blue. And our last two examples have reds as what's being left over, and we know that blue is what's excess, so those would be wrong as well. So our answer would be C. Okay, So let's now consider a chemical process, because that's what we're going to be using this concept for, of limiting reactants, is for chemical processes. So here we have hydrogen gas reacting with chlorine gas, creating hydrogen chloride. So imagine combining 3 moles of hydrogen gas and 2 moles of chlorine gas. When we're doing limiting reactant problems and we have balanced equations, the approach for determining the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. So we start off our reaction with 3 moles of H2 and 2 moles of Cl2. Once one of those is used up, that's as much HCl that we can form. So what we can do is use our mole-to-mole ratios to calculate how much HCl would form for each reactant. So the reactant yielding the lesser amount of product is the limiting reactant. So let's look at how we do that. So we started with 3 moles of H2. So for each reactant, we're going to calculate how much HCl we can form. So if we started with 3 moles of hydrogen gas, we can use our balanced equation to convert from moles of hydrogen gas to moles of HCl. Moles of hydrogen gas is in the bottom of our equivalency so that it can cancel, and we're left with moles of HCl. So if I reacted all 3 moles of hydrogen gas, I would get out 6 moles of HCl. We can do the same thing for the 2 moles of Cl2, where we use our mole-to-mole ratio, again putting moles of Cl2 on the bottom to cancel out our units appropriately. And we get out that if we reacted all 2 moles of chlorine gas, we would get out 4 moles of HCl. And our rule for limiting reactants says, well, whatever produces the lesser amount of product is our limiting reactant. Because this is saying that after I use up all 2 moles of my Cl2, the maximum amount of HCl that I can make is 4. Once I've used that up, I can't create any more moles, so I can't get to 6 moles of HCl. So the Cl2 will be consumed once 4 moles of HCl are produced. That means that we have unreacted H2 that will remain once the reaction is complete. This means that Cl2 is the limiting reactant because it produced the lesser amount of product, and H2 is the excess reactant because we're going to have some H2 left over. We can then calculate how much of the excess reactant is left over. So what we can do is convert the minimum mass or mole amount produced by the limiting reactant to the moles of the excess reactant. Then, if needed, we have to convert moles of excess to mass of excess depending on what the problem gives us. And this is the amount of excess reactant used up in the reaction. So we're basically saying I'm going to take the lesser amount of my product, okay, that was produced by my limiting reactant, and I'm going to work backwards and determine how much of my excess reactant I actually used up. Then what we can do is take the difference between the amount of the excess reactant we started with and subtract off the amount of excess that was actually used. So if we relate this back to our hot dog example from earlier, our amount of excess reactant that we started with, well, that would be our hot dogs. We started with 10 of them, but my buns limited the number that I could use, so I only ended up using 8 of those hot dogs because I only had 8 buns. So I only used up a partial amount of those hot dogs. So if we take the difference between those numbers, we know that we have 2 hot dogs left over. So let's do that for our example of hydrogen and chlorine. So we said that the maximum amount of HCl that we can produce is 4 moles. So we start with 4 moles of HCl. And what we want to do is now convert that value back to our excess reactant. So our balanced reaction, if I go back to it, had 2 moles of HCl and 1 mole of H2 gas, remembering that H2 was our excess reactant. So we have 2 moles of HCl for every 1 mole of H2. So to make 4 moles of HCl, I only had to use up 2 moles of H2. I started with 6 moles of H2, so to find my excess left over, we take the 6 moles that we started with. Was it 6 moles? No, 3 moles. I'm sorry, 3 moles. There we go. 3 moles of H2 that we started with. We subtract off the 2 moles of H2 that we used up, meaning I only have 1 mole of H2 left in my reaction, or in my reaction vessel. That is how much is left over, unreacted. So let's keep practicing this. How many moles of water could be made from 5 moles of H2 and 3 moles of O2? So I have the balanced reaction here, and we're saying if I'm mixing together 5 moles of hydrogen gas and 3 moles of oxygen gas, what is the maximum amount of water that we can create given that one of these reactants is going to limit us? So what we want to do is start off with our molar values of each reactant. So we're going to start first with 5 moles of H2, and we're going to convert that to our product, our water. So our mole to mole ratio for H2 and water is 2 to 2. So I put 2 moles of H2 on the bottom and 2 moles of H2O on the top. That'll cancel out our H2s, and we'll be left with 5 moles of water. Now we go to our 3 moles of oxygen and do a similar conversion. Instead of having moles of hydrogen gas, though, we're going to do 1 mole of oxygen gas for every 2 moles of H2O. And that gives us 3 times 2, which is 6 moles of H2O. So we've taken both of our reactants and determined how much product they could produce if they fully reacted. And whichever one produces the lesser amount of product is then the limiting reactant. So the lesser amount of product is 5 moles of H2O, meaning our limiting reactant is H2. Now remember, this is called limiting reactant. So one of your reactants has to be what's limiting. So sometimes I'll see students that convert it to the product and then say that the product is limiting because they see that value there. Remember, we're dealing with just the reactant. So whatever created that lesser amount of product is what is limiting that reaction overall. So I'm only going to create 5 moles of water because I used up all 5 moles of my hydrogen gas. This means that O2 is excess. Which brings us to our next question. For the same reaction, okay, what is the excess reactant? Well, we just said that that is O2, so we know that our answer is going to be one of these two. And how much of it is left over? So we said that the maximum amount of water that we can make is 5 moles. So we start off with 5 moles of H2O. And we want to convert that now to our excess reactant. So I want to convert it back to O2 to see how much O2 I actually needed to create that amount of water. So we're going to use our mole to mole ratio. We have 2 moles of water on the bottom because we're canceling it out. We have 1 mole of oxygen in the top because that's our excess. So 5 divided by 2 is 2.5 moles of oxygen gas. So I only needed to use 2.5 moles of oxygen to create those 5 moles of water. So that's how much we needed to use up. But I want to know how much is left over. So this is used up. So our original problem says, well, I started with 3.0 moles of oxygen and I used up 2.5 moles of oxygen. So how much is left over? Well, it's the difference of those two. So we take 3.0 moles of oxygen and subtract off the 2.5 moles of oxygen that we used, and we have 0.5 moles of oxygen left over. So our answer for this would be B. Now I want to show you another way of doing this problem that gets us the same answer. It just does it in a reverse order. So, and I oftentimes see students doing it this way as well, just because it makes more sense in their brains as opposed to the other way. So there are multiple ways that you can solve these types of problems. I believe your textbook does show a different way. So what we can do to find the amount of excess left over is we can take these two amounts of our product and we can find the difference between those, because that's basically saying, well, here's how much I could have made and here's how much I actually made. The difference is then going to be related to the excess reactant. So what we can do is take that 5.0 moles and subtract off the 6.0 moles. We'll take that absolute value because we can't have a negative mole value. Okay, and we get that the difference between them is 1.0 moles of H2O. We can then take that difference value and convert that to our excess reactant in order to see how much was unused in the reaction. So we take 1 mole of water, we do our mole to mole ratio, so I have 1 mole of O2 on the top and 2 moles of H2O on the bottom. Again, that comes from my balanced reaction. And 1 divided by 2 is 0.5 moles. Oops, not H2O, of O2. So that again gets us the same answer. It's doing the same steps, just in reverse. So in the previous version, I found the moles of excess and then I subtracted. Here I did my subtraction first and then converted to moles. It's the same concept, but sometimes our brains just think about it differently and see the concept differently. And those are the two ways that you can visualize this concept, at least through the math. And the best way to learn this is, again, through practice. And if you haven't noticed that from our lectures so far, we love to practice because that does show us how to do all these problems over and over again. So let's keep practicing. Our next problem says nitric oxide reacts with oxygen gas to form nitrogen dioxide. In one experiment, 0.885 moles of NO is mixed with 0.514 moles of O2. Determine which of the two reactants is the limiting reactant. Calculate also the number of moles of NO2 produced. So we're going to set up a similar problem here as we did with our previous examples, where we're going to take our moles of each reactant and convert it to moles of product. And we have the balanced reaction already. So we're just going to start with each reactant and convert it to our product of NO2. So we start with 0.885 moles of NO, and we convert that to moles of NO2. So I put moles of NO on the bottom so that it cancels, moles of NO2 on the top so that I have that unit left. I go to my balanced reaction and see that both of those values have a coefficient of 2, so this would be a 2 to 2 ratio. So we get moles of NO2 to be 0.885 moles of NO2. We then go to our other reactant of O2, which starts off with 0.514 moles of O2, and we now use our ratio to convert that as well. So we put moles of NO2 on top, moles of O2 on the bottom so that it cancels. We know our coefficient for NO2 is 2, and our coefficient for oxygen gas is 1. So we're going to take 0.514 and multiply that by 2. So we get 1.028 moles of NO2. So we look at our two values for our products, and the lesser of the two is what's limiting. So the lesser amount was 0.885 moles of NO2. That was created by NO, nitric oxide. So NO is limiting. Then it says also calculate the number of moles of NO2 produced, which we already did through this process. Now your textbook does show a different way, and I believe Alex shows this way as well, but there are multiple ways to do these problems. I personally find going from reactant to product the easiest way because most of these questions are usually asking for how much product is produced, so this is a direct way. Your textbook does show a way where you go from reactant to reactant, so you go from moles of NO to moles of O2, and then in your second reaction, moles of O2 to moles of NO. And this basically tells you the moles of each reactant that are needed to complete the reaction, and whichever one you don't have enough of is then your limiting reactant. I personally find this a very roundabout way of finding the limiting reactant because the next step after this is then to convert to your product, which again is just an extra step that's not needed when you can go directly from each reactant to product, and that also tells you the limiting reactant because they're all coming from the same balanced equation. So just keep that in mind as you're doing your practice through your textbook or in Alex, as it may show a different way where it's going from reactant to reactant, and that is a totally acceptable way to do these problems. But the way that I'm showing it as well, where we go from reactant to product, is equally as acceptable and gets us to the same numbers because all it's doing is using our multiple ratios in the same way. Okay, since they're all coming from the same balanced reaction, the ratios work out the same way. Okay, so there are multiple ways that we can figure out these problems. Okay, let's keep practicing. So, what I want you to do is I want you to pause your own video and try these problems on your own. Now, the first thing you're going to have to do for each of these is write out the balanced reactions. We don't have the balanced reactions for these two problems, so you're going to have to write them out first. So again, we have to make sure we're mastering balancing chemical equations, because if we don't have the correctly balanced equation, then we don't have the correct ratios. And if we don't have the correct ratios, then we don't get the correct product. Okay, so we need to make sure we can balance these equations first and then use those ratios to find our limiting reactant. So pause your video, take some time to go through these two problems, write out their balanced reactions, and try to figure out their limiting reactants. our first example, the balanced equation, is a combustion reaction. So the balanced equation comes out to 2C2H2 plus 5O2 goes to 4CO2 plus 2H2O. Now this reaction, you would have to use an intermediate fraction like we saw in our previous lesson. So that's how we were able to get the 5 in front of the O2. So just keep that in mind if you were stuck balancing and got to the oxygen and said, how do I make a 2 and do a 5? That's where we can use our intermediates and go from a fraction to a whole number. Okay, so now that we have the balanced chemical equation, we want to find out what the limiting reactant would be. Now for this, we have two products, so what we can do is one of two things. We can convert each reactant to just one product, or we can convert each reactant to both products. Either way you do it, you're still going to find the same results of what's limiting, okay, because of those multiple ratios. They all relate to each other. So let's start out with going from 2 moles of C2H2, and let's convert that to moles of CO2. So we have 2 moles of C2H2 goes to 4 moles of CO2. So we have 2 times 4 divided by 2. So we get out 4 moles of CO2. We can do the same thing with our moles of oxygen. We can do 1.0 moles of O2. For every 5 moles of O2, I get out 4 moles of CO2. So we get 1 times 4 divided by 5, that ratio. So we get out 0.8 moles of CO2. So the lesser amount comes from O2. So we could say that O2 is limiting. Now we can check our work, always good to check our work, and convert it to our other product of water. So we start off again with the same amount of reactant, and now we're going to convert it, instead of CO2, convert it to water. So that's just 2 moles. And then for oxygen, we start again with 1 mole of O2. And for every 5 moles of O2, we get out 2 moles of H2O. So we do 1 times 2 divided by 5. Oops, not 59. There we go. So that gets us out 0.4 moles of H2O. So again, that shows that O2 is limiting. And for this problem, it just asked for the chemical formula, so you would just type in O2. Okay, next up we have solid aluminum and chlorine gas react to form solid aluminum chloride. Suppose you have 11 moles of aluminum and 2 moles of chlorine in a reactor. Calculate the largest amount of AlCl3, aluminum chloride, that could be produced. Round your answer to the nearest 0.1. Now, this problem does have some word trickery in there. Because it's a limiting reactant problem, the largest amount of aluminum chloride that can be produced would be the one that produces the lesser number. Okay, so remember that whatever reactant produces the lesser amount of product is then limiting, because that's the maximum amount of product that we can create given our reactants. Okay, so it's a little bit of word trickery in there. So we're going to start this problem out by balancing our chemical equation. So we have Al plus Cl2 goes to AlCl3. To quickly balance this, we would put a 2 in front of the AlCl3 and a 3 in front of the Cl2 to balance out those chlorines. Okay, one has 2, the other has 3. Since there's nothing easy to balance there, we're just going to multiply by those values to get 6. And because we added a 2 in front of the aluminum on the product side, we're going to put a 2 in front of the aluminum on the reactant side. So, again, the importance of a balanced reaction. If we didn't balance it, then we wouldn't have any multimole ratios. It would all be 1-to-1, which would not be correct. So we have to have the balanced equation first. So now that we have the balanced equation, we can use our values that we're starting out with. So we have 11 moles of aluminum that we're going to convert to aluminum chloride through our multimole ratio. So 2 moles of aluminum goes to 2 moles of AlCl3, aluminum chloride. So we get out 11 moles of aluminum chloride. We then do our next reactant, which is 2 moles of Cl2. And we use our multimole ratio, which is for every 3 moles of Cl2 used, we create 2 moles of aluminum chloride. So we take 2 times 2/3, and we get out 1.33 moles of aluminum chloride. So, because based off of our reactants, the amount of reactants that we have, the maximum amount or the largest amount of aluminum chloride that we can produce from this reaction is 1.33 moles. Okay, it's not 11 moles because I don't have enough chlorine to produce that much aluminum chloride. So since the chlorine is limiting us, I can only create 1.33 moles of aluminum chloride. So my answer for this, rounded to the nearest 0.1 mole, would be 1.3 moles of aluminum chloride. So don't let the word trickery here change how you think about these limiting reactant problems. Okay, now let's pause and try this one. This one is similar to all of our previous examples, except now I'm bringing in mass, and I want to get out mass. Now this is no different from what we've been doing in previous sections, previous lessons, going from grams to moles. We know how to do that. We've been doing that for multiple chapters now. Okay, so the first thing that we're going to want to do is, instead of going right into our multimole ratio to compare our reactants to our products, we first want to convert grams to moles so that we can properly use our multimole ratio. So the first thing we're going to do is we're going to start with the 48.2 grams of HCl, and we're going to convert that to moles. So we're going to use the molar mass of HCl, so 1 mole of HCl is equal to 36.46 grams, and again, I'm just getting that from the periodic table. So we take 48.2 and we divide that by 36.46. And that gets us out 1.32199 moles of HCl. So I now have my moles of one reactant. The problem also gives us 0.86 moles of our other reactant, MnO2. So now what we want to do is determine the limiting reactant, the reactant that will be used up first, and then we want to find the number of grams of Cl2 that will be produced from that limiting reactant. So we've set up the problem to start off just like our previous examples, so pause your video and complete this problem. So we have our mole values of each of our reactants in a balanced chemical equation, so we can convert from moles of reactant to moles of product. So we have moles of HCl and we want to get out Cl2. That's what our question is asking us for. You could have gone to any reactant. Okay, you could have gone from Cl to MnCl or to water. It doesn't matter. But since the problem is specifically asking for the mass of chlorine that will be produced, it's just good practice to do your first conversion to the product that the question is asking for. But again, like we saw in our previous examples, you can go to either product, any product, and it'll still tell you what's limiting. So we're going to convert this from 4 moles of HCl to 1 mole of Cl2. So we get this divided by 4, right? And we get 0.3305 moles of Cl2. For MnO2, I have a 1 mole MnO2 for 1 mole of Cl2. So we get out 0.86 moles of Cl2. So this suggests that because this is the lower amount, HCl is limiting. So that answers our first question of which reactant will be used up first. HCl is our limiting reactant, and that will be used up first. The second question is now asking for the grams of chlorine that will be produced. Well, we have moles of chlorine, so we can start off with that 0.3305 moles of Cl2, and we can convert that to mass. So we have that in 1 mole of Cl2, we have how many grams? Well, the molar mass of chlorine is 35.45. We're going to multiply that by 2 because this is diatomic. So it's 70.90 grams. So we'll take that 70.90, multiply it by 0.3305, and we get out 23.43245 grams of Cl2 that will be produced. Now for sig figs, because we did not use the mole value of MnO2 to determine our mass of chlorine, I went from 48.2 to find this answer. We would actually only consider the 48.2 as our significant figures value. So this would actually come out to be 23.4 grams of Cl2. So the MnO2 did not contribute to calculating the mass of chlorine that was produced because that's our excess reactant. So its value does not come into play in the significant figures determination because its number was not used to find the final value.